Unit Overview. In this unit, we introduce an important data structure called tree, which is extensively used to represent hierarchical relationship. This unit begins with an introduction to general trees and elaborates basic definitions and tree terminologies. It mainly focuses on binary trees and their variant forms, namely binary search tree and expression tree. It provides exhaustive description of binary trees, including basic concept and actual implementation of tree operations. Unit Objectives. After completing the unit, you should be able to understand the vocabulary and terms relating to tree data structure. Describe properties of general trees and their applications. Explain the distinguishing features of binary search trees, heap, expression trees, red-black trees, and decision trees. Understand the difference between pre-order, in-order, and post-order traversal of binary tree. Become conversant with the implementation of traversal algorithms using recursive procedure. Understand the significance of binary search trees for sorting and searching problems. Recognize significance of balanced trees and unbalanced trees and the associated performance issues. Introduction to trees. A tree is a data structure in which data elements have hierarchical relationship. There are several ways of describing the internal structure of a tree. Formally, we can define a tree data structure as a collection of data elements called nodes, such that the collection has a special node called root, which provides an entry point to the tree data structure. The nodes are connected together with edges or paths. There is exactly one path from the root to any node in the tree. A tree data structure is often depicted by means of a diagram. Unlike a natural tree, a tree data structure is shown to grow from top to bottom, with the root at the top and leaves at the lowest level. A node is represented by a circle, oval, or rectangle. It is usually labeled with the data value contained in the node. The edges are shown by the slanted lines. By convention, tree is portrayed from top to bottom. The direction of edges is therefore omitted. Figure shows an example of tree data structure. In this structure, A is root node. E, M, N, G, H, I, J, K, L are leaves. All other nodes are the internal nodes. Basic definition and terminology. The structure and properties of a tree structure are described by using a special vocabulary which is borrowed from mathematical graph theory and family trees. Most algorithms for trees use this terminology. We therefore have a closer look at these terms. Parent node. In the tree hierarchy, a node directly above a given node is called parent node. C is the parent node of H, I, and J. The only exception is the root node, which has no parent. Child node. A node which is directly below a parent node is called child node or simply a child. For example, C is the child of root and H, I, J are children of C. Siblings. All children which have common parent are collectively known as siblings. Thus, H, I, J are siblings of C. Likewise, B, C, and D are siblings of root. If all siblings appear in definite order, say in alphabetical order, the tree is called ordered tree. The tree shown in this figure is in fact an ordered tree. Ancestors. Recall that in a tree structure, a node has a unique path to the root node. All nodes which appear on the path from a given node to the root node are called ancestors of the given node. For example, ancestor of M are F, B, and A. Descendant. A descendant is a child of a node or descendant of the child. All of the descendants of a node N are called a subtree rooted at N. In figure, the subtree rooted at B consists of nodes B, E, F, G, M, and N. A subtree may comprise a single leaf node. As we shall see later, the notion of subtree is of great help in partial processing of data contained in a subset of nodes. Level of tree. Obviously, the nodes of a tree are organized at different levels. By convention, the root node is at level 0. The children of root are at level 1. The children of root are at level 2, and so on. Notice that in figure the nodes B, C, and D are at level 1 and nodes E, F, G, H, I, J, K, and L are at level 2. The leaves M, N are at level 3. Height of a tree. The maximum level of a node in a tree is called height of a tree. Thus, the tree structure in figure has height 3. As we shall see later, the height of a tree plays a crucial role in determining the performance of search algorithms. A tree with the shorter height can be searched faster than an equivalent tree with greater height containing the same data elements. From the preceding discussion, we conclude that a tree data structure has two important characteristics which distinguish it from other data structures. First, unlike a stack and a queue, a tree is a non-linear structure. This implies that a data element in tree has more than one successor, which can be depicted in hierarchical fashion in 2 dimensions. Second, the defining property of a tree is the existence of a unique path from root to any of the tree nodes. This also implies that any node in the tree has a unique parent except the root node. If there is more than one path or more than one parent to a node, or there is no path, then the structure is not a valid tree data structure. It belongs to the data structure called graph. Figure shows an illustration in which node E has two parents, B and C. Also note that G has two paths to the root, namely G, E, B, A and G, E, C, A. Thus, we conclude that data structure is not a tree. Forest. We have seen that a node which has no path to the root of a tree is not considered part of the tree. This situation leads to the notion of a forest, which is defined as a set of disjoint tree structure. The disjoint property implies that there is no explicit path linking one tree to another. For example, if we remove the root node, we have a set of 3 disjoint trees shown in figure. Here, the forest is a set of 3 trees. Classification of trees. The tree structures are classified on the basis of maximum number of children permissible to be attached to a parent node. If in a tree a parent has 0, 1 to n children, it is called n-ary or n-way tree. A ternary tree, for example, is the one in which each node can have up to 3 children. If an n-ary tree contains nodes in specific order, the tree is called multi-way tree. In this case, each node contains a set of keys which determine range of values held by child nodes. For example, in a ternary tree, a node may contain keys A, H, and T to imply that the first child would contain a character in the range A to G. Second child would contain character in range H to S, and third would contain characters in range T to Z. Multi-ways trees are frequently used in modern database management system to facilitate rapid searching of indexed records. In order to improve the performance of search operations, the height of tree is kept to be minimum by balancing the levels of subtrees. The resulting trees are often called as balanced trees. The term B-tree is often used to describe such trees. B-plus tree is a variant of B-tree, in which all the leaves are linked by pointers to facilitate sequential searching, in addition to normal random searching. Indeed, B and B-plus trees are cornerstones of all modern data file systems and database management systems. Simpler versions of B-tree are used in some applications. Two such variants are known as 2-3 tree and 2-3-4 tree. The former contains 2 to 3 nodes per child and later 2 to 4 nodes per child. Figure shows a small 2-3 tree. A binary tree is the simplest form of tree data structure. In this structure, each node can have at most 2 child nodes. We shall study in great detail the binary tree structure in the subsequent section of the unit. For now, let us briefly look at some of the applications of binary trees. Application of trees. Many hierarchical data structures, analogues to trees, are commonly encountered in our daily life. A familiar example is the organization chart of a large department or company in which the hierarchy of the organization is shown. The root node shows the head or CEO. The children of root are usually the senior management, which are followed by middle or junior executives. The line or operation level staffs are generally exhibited at the leaf nodes. By systematically scanning the trees, from top to bottom, we can list all positions at different levels in the organization. Another common example of tree data structure is table of contents of a book or a document as shown in figure. The title of book is at the root. The book is generally organized into several chapters. Each chapter may be further organized into sections, and the sections may in turn be divided into subsections. Using one of the tree algorithms, we can print the table of contents of the book with chapters, sections, and subsections appropriately indented as shown. Perhaps the most common example of tree familiar to computer user is the structure of filing system in operating systems such as Unix, Windows, and Mac. Information and content of a set of files residing in the computer are organized in a hierarchy of directories and subdirectories as shown. The root of the tree represents the root directory. The data files are represented at leaf levels. By traversing tree, we can determine the contents of files in each subdirectories and print their size. Binary trees. We now turn to an important data structure called binary tree, which is the main focus of the present unit. Binary trees were introduced briefly earlier as an ordered tree structure in which each node can have at most 2 children. The first child is referred to as left child and second child as right child. Figure portrays an example of binary tree. Notice that binary tree is an ordered tree in which a distinction is made between left and right child nodes. Consider, for example, the 2 binary trees shown. Although both trees contain identical data elements, structurally these are treated as different trees. Full binary tree. A binary tree in which all nodes exist right up to the bottom level is called full binary tree. In other words, in full binary tree, no internal nodes are missing. Figure shows an example of full binary tree. Notice that in full binary tree, number of nodes at level 0, 1, 2, 3 are 1, 2, 4 and 8 respectively. We can use this observation to compute the total number of nodes in full trees of given height h. If n is the number of nodes, then by evaluating the sum we have the formula, or after some simplification and taking logarithms of both sides we can express the tree height in terms of number of nodes as, for example, the full tree in figure consists of 15 nodes. The height of tree is 3. Complete binary tree. A full binary tree represents an ideal situation. Such trees are rarely found in actual applications. Another structure which is close to a full binary tree is called complete binary tree. In a complete binary tree of height h, we have all nodes up to level h-1 exist. In other words, the tree is full up to level h-1. Some nodes may be missing at level h or at bottom level. All nodes at the bottom level must exist in leftmost positions. Figure shows an example of a complete tree. Notice that at the bottom level, some of the nodes are missing. The filled nodes at the bottom, namely I, J and K, are in the leftmost position. By way of contrast, this figure shows a non-complete tree because the available node at the bottom level are in the rightmost position rather than in the leftmost position. The distinction between a full tree, complete tree and non-complete tree can be viewed more vividly by looking at the triangle arrow to the tree structure. Figure shows such triangles. The missing nodes are represented as unshaded area of the triangle. Types of binary trees. Binary trees are often classified on the basis of type of data structure contained in the nodes. Generally, 4 types of trees are used in different applications. These are characterized as ordered trees, expression trees, heaps, and decision trees. Ordered search trees. These are the most common trees which are widely used in several searching and sorting algorithms. The ordered tree is structured such that the data values in the left subtree are less than data values in the right subtrees. The data can be numbers, characters, strings, or key field. Figure shows an example of binary search tree. Notice that the value 50 contained in the root node is greater than all values contained in the left subtree, which contains 40, 30, 35, and 31. Also, root value is less than all the values in the right subtree comprising 70, 80, 65, and 75. This principle applies to all the nodes. We shall explore binary search tree in greater detail in a later section. Expression trees. Expression tree is structured to represent an arithmetic expression in a hierarchical manner. Each node contains either an arithmetic operator or an operand. For example, the expression a minus b and b minus a are represented as shown in figure. The expression for a complex arithmetic expression such as is shown in figure. Notice that operands in the expression tree always appear as leaf nodes and operators are contained in the internal nodes or in root node. In a later section, we shall examine how to construct an expression tree for an arithmetic expression. Heap. A heap is a special kind of binary tree which is structured such that the data value in each node is greater than the values contained in its left and right subtrees. Figure shows a heap. Notice that the value 80 in the root is greater than all values contained in the left and right subtrees. In general, this is true of all the subtrees rooted at different nodes. A heap can be used to represent a priority queue. Recall that in priority queue, the highest data value is always contained in the root. However, after removing the value held by the root node, the tree must be restructured to maintain the heap properties. Heaps are also used in sorting algorithms. Binary decision trees. A binary decision tree is structured to represent a sequence of if-then-else logical conditions and the resulting actions. Each node contains a test value or the appropriate action. Figure shows an example of a decision tree. In this representation, C1 through C6 are conditions and A1 through A7 are actions or conclusions. Decision trees are often used to represent a chain of rules for searching a knowledge base used in artificial intelligence or expert systems. They can also be used for parsing of logical expression in high-level programming languages. Implementation of binary trees. Implementation of a binary tree involves storage representation of nodes and coding of associated operations. We first consider the storage structure aspects of the implementation. Two common approaches are used to define tree structure. One method is known as linear representation or vector representation, which utilizes a one-dimensional array to store node values and pointers. The other method is known as link representation or pointer representation. It uses dynamic allocation of storage for tree nodes and associated pointers. We now examine these implementations. Linear representation of binary trees. In linear representation, we store node values and pointers in array cells. To implement the array-based structure, we first define a structure of node in C++ as we use a single array of C++ struct data type. Each struct cell contains data and pointers to child nodes. Then we create an array of nodes to represent the entire tree. We populate the tree by assigning node values and appropriate indexes. For example, the first node of a tree array would be collective values as shown. An implementation using single array is shown. the corresponding binary tree is also shown. Notice that left child and right child columns contain indexes of the corresponding left and right children in array. For example, for data C, the left child index is 6, which is the index for data D. Thus, D is the left child of C. If addition and deletion are made to the tree, the corresponding indexes would also change. In order to keep track of the root node and vacant cells, we would need to use two variables, say top and free, which point to the root cell and a list of vacant cells. We can also adopt a simpler approach to store elements of a tree in a single array of characters. It is based on a numbering scheme for the nodes of a binary tree. Figure shows a sample binary tree and its compact representation by an array of characters. The number next to a node represents the index value. The missing nodes are shown in the broken circle as shown. The nodes are numbered from top to bottom and left to right. Root is numbered 1. Its left and right children are numbered 2 and 3. The nodes at next level are numbered 4 through 7. In order to create an array for tree structure, we place node values in array cell according to the number assigned to the node. If a node is missing in the tree, the corresponding cell in the array is kept blank. The compact array representation is efficient if the tree is full or complete. Otherwise, a lot of space for missing nodes would be wasted. Consider, for example, a right-skewed binary tree in which all the nodes occur at the right children. Figure shows such a tree and the corresponding storage array. Notice that to store fewer elements of tree, we need an array of 15 cells. In this case, over 65% of the allocated space is wasted. Advantages and disadvantages of linear representation. We conclude that array provides a simple and efficient mechanism for representing binary trees. Given the location of a child, we can have direct access to the content of a node. Nonetheless, addition and deletion of node is rather inefficient because it would involve data movement within the array. Also, a lot of space is wasted if the binary tree is skewed or incomplete. This representation is useful if the number of missing nodes is small. Linked representation of binary trees. Linked list is the most common representation of binary tree. In this representation, the nodes have explicit pointers to the child nodes. Thus, each node contains the tree data element and addresses of the two children. Figure shows a linked representation of a simple binary tree. If a node is missing, the corresponding address value in the parent node is set to null, shown as / in the diagram. In linked representation, the storage space is allocated dynamically. The nodes are created as the need arises. The storage space is released when the node is deleted. For linked representation, we define two classes, one for the node and other for the tree structure and its associated methods. In C++, the class representing a node is defined as: it contains node data of character type. Left is pointer to left node. Right is pointer to right node. The structure of a class representing the tree would depend on the type of binary tree and its associated operations. Binary tree traversal. Traversing is the process of visiting the nodes of a tree in systematic way in order to process the data contained in the node. Each node should be visited exactly once. There are three standard ways of traversing, which are called pre-order traversal, in-order traversal, and post-order traversal. Pre-order traversal. The pre-order traversal is based on the following algorithm. Visit the root node first, traverse the left subtree in pre-order, traverse the right subtree in pre-order. Figure shows the traverse mechanism for a simple tree consisting of just 3 nodes. Root A is visited first. The left subtree B is visited next. The right subtree C is visited last. Thus, pre-order traversal is A, B, C. This figure shows the pre-order traversal of a bigger tree with 8 nodes. To traverse the tree in pre-order, we start at the root node A. Then traverse the 2 nodes B and D in the left subtree T1. Then we move to the right subtree T2, which contains a left subtree T3. Next, we first visit the root node C of right subtree. Then traverse the root node E of tree T3. This is followed by its visit to G and H. Last of all, we visit node F. Pre-order traversal of this tree is A, B, D, C, E, G, H and F. In-order traversal. The algorithm for in-order traversal is: traverse the left subtree in order first, visit the root node, traverse the right subtree in order. Figure shows traversal of a simple 3-node tree. First, the left subtree B is visited. Next, root A is visited. Lastly, right subtree C is visited. Thus, nodes are visited in the order B, A, C. This figure depicts in-order traversal of a bigger tree. To traverse in order, first the left subtree T1 is traversed to visit D, B. Then root node A is visited. Next, left subtree T3 within the right subtree T2 is visited. It consists of nodes G, E and H. Lastly, remaining nodes C and F of the right subtree are visited. Thus, in-order traversal leads to visit sequence D, B, A, G, E, H, C, F. Post-order traversal. The algorithm for post-order traversal is: traverse the left subtree post-order first, traverse the right subtree post-order, visit the root node. Figure illustrate the traversal of a simple tree consisting of 3 nodes A, B and C. First, the left subtree B is visited. Next, the right subtree C is visited. Lastly, the root node A is visited. Thus, post-order traversal is BCA. Figure illustrates the post-order traversal of a bigger tree consisting of 8 nodes. In this case, first the left subtree T1 is traversed post-order. Then nodes D and B are visited. Next, right subtree T2 is traversed. It includes a subtree T3 consisting of nodes G, E and H. These nodes are visited in post-order G, E and H. Next, the remaining nodes of right subtree are visited, which include F and C. Last of all, root node A is visited. Thus, post-order traversal yields the sequence DBGHEFCA. Implementation of pre-order recursive traversal. We now examine the code to implement the recursive algorithm for pre-order traversal. A C++ interface for the tree is shown in figure. Each node would contain a single character. Further, it includes two methods, CRBT and BT. These are used to create the binary tree. It also contains pre-order method to traverse the tree in pre-order. The main operative methods for pre-order traversals are pre-order and pre. Pre-order function is called in main program. It passes the address of root node to the helper function pre, which implements the algorithm for pre-order traversal. Procedure is invoke helper function, visit node and print data. Traverse left subtree pre-order, traverse right subtree pre-order. The class methods are usually called from the function main in C++ program. The essential ingredients of main function are shown in figure. The detailed coding is shown in the demonstration that immediately follows. Implementation of in-order recursive traversal. You would recall that in in-order traversal, first the left subtree is traversed in order, then root is visited, and finally the right subtree is traversed in order. The necessary code for this algorithm is invoke helper function, traverse left subtree in order, visit node and print data, traverse right subtree in order. Implementation of post-order recursive traversal. In post-order traversal, first the left subtree is traversed post-order, then the right subtree is traversed post-order, and finally the root node is visited. The code fragment to implement the algorithm is invoke helper function, traverse left subtree post-order, traverse right subtree post-order, visit node and print data. Stack-based implementation of pre-order traversal. The implementation of recursive procedure for traversal of binary tree is simple. However, in the recursive algorithm, the underlying procedural steps are not visible. An alternative approach is to use an iterative procedure, which is intuitively more clear. In iterative procedure, we would need to descend and ascend to different parts of the tree. The address value contained in each node enables us to descend to right or left subtree. The iterative procedure is essentially stack-based. The algorithm for pre-order traversal of a tree in iterative way is: number 1. Push the address of root to stack and assign current node pointer P to the root. Repeat step 2 until P is not null. Number 2. Proceed down the leftmost subtree rooted at P. If there is any right node on the way, push its address onto the stack. Continue processing the nodes until the leaf node is reached and processed. Number 3. Pop the stack and assign the popped address to current pointer P. If P is null, exit. Otherwise, perform step 2. Let us consider an example of application of iterative procedure for pre-order traversal. This figure depicts a sample tree. Steps are summarized as: process A, push C, process B, D, pop C, push F, process E, push H, process G, pop H, pop F. Finally, the pre-order traversal is A, B, D, C, E, G, H, F. The code for iterative procedure for tree traversal is substantially more complex than the code for equivalent recursive procedure. In the former case, we have to deal with three classes representing tree node, stack, and tree structure. The interface for these classes are as shown. Here, B-tree class includes methods CRBT and BT to construct a binary tree. It contains stack preorder method to traverse the tree in stack-based preorder. Stack class utilizes an array of node objects to hold node data and pointer addresses. It contains push and pop method for storing and returning node data from stack. Code for the stack preorder method in the B-tree class is given in the demonstration. Stack-based implementation of in-order traversal. We can implement the iterative procedure for in-order traversal of a binary tree by using a stack. The algorithm based on the iterative procedure is: Number 1. Assign current pointer P to the root of the tree. Repeat step 2 through 3 until P is not null. Number 2. Proceed down the leftmost rooted at P, pushing onto the stack addresses of a node on the way. Number 3. Pop off the stack and process the pop node. If stack is empty, then exit. If the pop node has a right child, assign current pointer P to the right child and perform step 2. Let us explore how the algorithm can be applied to traverse a tree. Figure shows a sample tree. We follow these steps to traverse in order. Push ABD, pop DBA, push CEG, pop GE, push H, pop H, pop C, push F, pop F. Finally, the in-order traversal is DBAG, EHCF. The implementation of the iterative procedure for in-order traversal uses the set of classes called node, stack, and tree structure, which we presented in previous section. For the in-order traversal, we use a method named stackInOrder. The code for this method is shown in demonstration. Stack-based implementation of post-order traversal. The iterative procedure for post-order traversal is more complicated than the pre-order and in-order procedure presented earlier. Here, we have to save addresses of a node and its associated child. After popping a node, the right child are handled differently. In order to make a distinction between left and right child, we use some special symbols, say $, which is saved with the address of the right child. The algorithm for post-order iterative procedure is: Number 1. Assign a current pointer P to the root node. Then repeat step 2 to 3 until the stack is empty. Number 2. Traverse down the leftmost path of the tree root at P. At each node, push the address onto the stack. If there is right child, push it to the stack by flagging with $. Continue until the leaf node is reached. Number 3. Pop and process all nodes which do not have the flag $. If the stack is empty, exit. If a node with $sign flag is popped, remove the flag and assign current pointer to the right child. Perform step 2. Let us see how this algorithm is used to traverse a tree in post order. Consider the tree shown in figure. The necessary steps for traversal are summarized as push A $C B D, pop DB, pop $C, push C $F, push E $H, push G, pop G, pop $H, pop HE, pop $F, push F, pop FCA. Finally, the post-order traversal is DB GH EFCA. In order to implement the post-order iterations, we need to modify the node class to include flag, which can be $sign for a right child and space otherwise. The new class structure is shown in figure. It is renamed as snode to make a distinction. The code for implementing the post-order procedure using a stack is shown in demonstration. Binary search trees. The binary search trees were briefly introduced earlier. Each node of a BST contains a distinct data item which identifies the contents of the node. The data item is commonly referred to as node key. In a search tree, the keys of all nodes in the left subtree are smaller than the keys of all nodes in the right subtree. In practice, nodes of a tree can contain simple data type such as numbers, characters, or strings. Figure shows some examples of binary trees containing numbers and characters. In many practical problems, such as databases, the nodes of a tree consist of records comprising several fields. One of the fields is designated as record key or key for the node storing the record. Figure depicts an example of search tree which stores personal records. In this example, personal identification number is the node key. Other fields are name and salary. We emphasize that a given set of data item can be arranged in a binary search tree in several ways. Figure shows how the set of characters A, B, C, D, E, F, G can be represented in binary search tree with different tree structures. Notice that two of the structures are skewed to left or right. In these cases, the binary tree actually degenerates into a linked list. Later on, we shall see that the overall tree structure is determined by the order in which nodes are inserted into the tree. Operation on binary search trees. We can specify operations to create, manipulate, and visit nodes of a binary tree. The traversal methods considered in the previous sections are also applicable to binary search trees. In addition to the basic operations for a search tree, it includes create, destroy, and isEmpty methods. Inserting a node into binary search trees. In order to insert, we have to take two things into consideration. First, we need to find a location in the tree structure where a new node can be placed. To maintain the binary property of the tree, the new node must always be added as leaf node. Second, after insertion, we must ensure that binary search property is maintained. This implies that key of each node must remain greater than all keys in the left subtree and less than all keys in the right subtree. Example. Consider, for example, a binary search tree shown in figure. To insert a new node, say Q, we proceed as follows. Beginning with the root, we compare Q with the keys of a node. First of all, Q is compared to S. Since it is less than S, we move to the left child which contains H. We compare Q and H. Since Q is greater than H, we descend to the right child which is G. Again, Q is compared with G. Since it is greater than G and G have no children, we attach Q to G as its right child. Notice that after insertion of Q, the binary search property is preserved. Implementation of insertion procedure. A node can be inserted into a binary search tree by using an iterative or recursive procedure. The iterative procedure uses a loop to perform comparison of keys with the keys of left or right children until a leaf node is reached. If the keys are equal, the loop is terminated with some prompting message. In order to develop the code for insertion operation, we assume that each node of a binary tree stores a character string of some fixed size. The structure of node class is shown in figure. T-node class contains node data. It contains pointer to left child. It also contains pointer to right child. The complete code for iterative insertion procedure is given in reference notes. Searching a binary tree. Searching operation is performed to determine whether or not a node exists in a tree with the given key value. If search is successful, some kind of further operation is performed on the searched node, such as printing or updating the node contents. The algorithm for the search operation is similar to one for insertion operation. The search can be carried out interactively or recursive way. In either case, we start with the root node. If the search key matches with the key of root node, the search process is terminated. Otherwise, we proceed to search the left or right subtree according to the key is less than or greater than the node key. If at any stage the key matches with the key of some node, the search process is terminated. If the leaf node is reached and no matches occur, the search process is terminated as being unsuccessful. Example. Consider, for example, a binary tree shown in figure. Suppose we want to know if a node with key values Q exists in the tree. We start with the root node and compare Q to key value S. Since Q is less than S, we proceed to the left child which has key N. Since Q is greater than N, we move to the right child which has key M. Since Q is greater than M, we descend to the right child which has the matching key. The search is finished. Next, suppose we look for a node with key K. The search path is shown in figure. In this case, the search is not successful because after traversing N, H and J, we end up with a leaf node whose key J does not match with the described key K. Sometimes we are interested in finding the largest and the smallest key stored in a tree. The search for these keys can be performed easily. To find the minimum key, we start with root node and proceed along the extreme left path until we reach the leaf node which would contain the lowest key. Likewise, to find the maximum key, we proceed, beginning with root, along the rightmost path until we reach a leaf node which would contain the maximum key. Implementation of search operation. As pointed out earlier, a binary search tree can be searched by using either iterative or recursive procedure. The iterative procedure is intuitively more clear because it reflects the searching steps as we descend the tree. A code fragment for search operation is given in reference notes. Performance of search operation. We have seen that in performing search on a binary tree we descend from one level to next level. Further, at each level we process exactly one node to match keys. In best case scenario, the search value would be found in the root node. In the worst case, the search process would be continued down to the bottom node. Thus, we conclude that maximum search time in worst case is proportional to the height of a binary tree. In our earlier discussion, we demonstrated that the height h of binary tree is given in terms of number n of tree nodes by the formula. Since runtime for search function is proportional to height, we can say that in big O notation, the time efficiency is O log n plus 1 minus 1. Recall that according to big O rules, the additive constant can be ignored in runtime expressions. We therefore conclude that in worst case, the performance of binary search tree operation is O log n. The binary search method is far more efficient than other search methods normally used with arrays or linked lists. For example, with an array containing 1 million unordered data items, we may have to perform on average 500,000 comparisons. If the same data is organized into a binary search tree, the number of comparisons would be around 20. However, for maximum performance, it must be ensured that in building a tree structure, the height of tree is kept to barest minimum. If, for some reasons, the trees become unbalanced and skewed to left or right, then it would degenerate into the linked list with height equal to the number of nodes. In this case, the performance of search operation would be O of n. Traversing binary search trees. The basic traversal operations, in-order, pre-order, and post-order can be used to process the nodes of a binary search tree. However, we are particularly interested in the in-order traversal because it produces sorted list of node keys. Figure shows the in-order traversal path of a sample binary search tree and the result of traversal. Notice that the visited nodes have keys in ascending order. Performance of tree traversals. In traversing a tree, each node is visited exactly once. Thus, if there are n nodes in the tree, then traversal time would be proportional to n. In addition, some time it would be needed to process the contents of each node. As a result, total time of tree traversal and visit is proportional to n plus c, where c is a constant. We conclude that efficiency of tree traversal is O n plus c or O n, ignoring constant c.